Welcome to my channel. Our channel has reached the 300 subscribers. To celebrate this event, I will add a lesson to the practical lesson playlist. In this session, we will talk about transistor. The transistor are the foundation stone to understand electronic and to make some useful project. Those transistors are the successor for the vacuum tube, those OLED amplifier. We have two major family for the transistor. We have the bipolar transistor, bipolar junction transistor (BJT), and the field effect transistor, the FET. For the BJT, we have two family. We have the NPN transistor and the PNP. We have here this is the sample of an NPN transistor. And this is the sample for a PNP transistor. This is the PNP transistor. So those transistors can function as a switch, electronic switch, or an amplifier. We have here every transistor has a 3-pin. All transistors they have a 3-pin. We have the base and the collector and the emitter. Here we have the base. This is the collector and this is the emitter. The arrow here point to the emitter. And this one we have here the emitter, here the collector, and here the base for the PNP. This is the NPN transistor and this is the PNP transistor. So we begin with the BJT and then we talk about the field effect transistor. To let this transistor switch, we must inject a current from the base. Here we will put the ground. Here we put the ground. So when we inject a small amount of current from the base, it will induce a current from the collector to the emitter. This is the base to emitter current, and this is the collector to the emitter current. This one is called IB, the base current, and this one is called IC, the collector current. To limit the current for the base, we must use a resistor here. We must use a resistor for the base, and to limit the current in the collector, we must use another resistor. This is the resistor. This resistor called RC, and this one is called RB. RB and RC. Because this junction, it works as a diode. So when we apply, for example, here a voltage over 0.6 volt, it will conduct the current. And to limit this current, we must use the base resistor. Because when we use, for example, here the characteristic, the curve for the PN junction, this is the, for example, the VBE, and this is the IB. When we apply a voltage here, the current will start to grow exponentially, and it may destruct this junction. So we must use a resistor to limit this current. We have a relationship between the collector current and the base current. We have here the formula. IC is equal to beta multiplied by IB. Beta is the amplification coefficient of the transistor. It's called also hash FE. for the PNP transistor, we must sink some current here from the base to let the current flow from the emitter to the collector. So here we must add the the base resistor, and here we must add the collector resistor. This is RC. So when we sink here a small amount of current, we get a current amplified here from the emitter to the collector. For the phase defect transistor, we have also a 3-terminal. This is the gate, and this is the drain, and this is the source. So to let this transistor conductive, we must apply here some voltage here. This transistor has a high impedance, high input impedance, so it doesn't need a flow of current as the bipolar transistor. Only a small amount of charge here to let the transistor conductive. And when this transistor is conductive, it's equivalent of a resistor, a small resistor called RDS on. This is RDS on. Now we will see the package of the transistor and some characteristics. For the package, we have a lot of package of transistors. We can begin with this OLED package, TO3. It has a metallic case, and this is for a power transistor. It's used inside OLED TV. We have also some plastic package like this one. This is TO126. We can find also those power transistor, TO264. And for small project, we use the TO92, this small one, for small power. Also, we can find this OLED metallic case for transistor, TO39. Now we will see why we use a transistor and how we will use them. As we said earlier, this transistor can work to amplify small current. It works as a switch or an amplifier. For example, if we need to switch this relay on, or to turn on this bulb or this motor, we need an amount of current, for example 1 amp or 200 milliamp. This can be derived by this tiny circuit. For example, this circuit is 74HC74. We can see the datasheet of the circuit. The maximum current that can source or give is 25 milliamp. 25 milliamp that can't activate this motor, for example. So we need to use a transistor. The transistor used depends on the amount of current we need, or power. For huge power we need this package, and for small power we need those tiny transistors. Those transistors are different with a lot of things. For example, if we need to make a project, we can see our voltage, our power supply. For example, for the BC 547, the maximum voltage between the collector and the ground and the emitter, the maximum voltage is 80 volt. For the BC 547 is a 50 volt, and 46 80 volt, and the 48 30 volt. If they have the same price, we can always buy the one which has the maximum voltage between the collector and the emitter. Although the transistor are, every transistor has this beta, this coefficient of amplification. So for the BC 546 or 47 or 48, we have a DC current gain, hash FE. It's between the 110 and 450, for example. This coefficient is not given precisely because it varies with the voltage of the collector and the temperature. We can, for example, try to measure this coefficient for this transistor. For example, we can use this coefficient with this tester. I will put the transistor inside this socket. We have 398. So in this region, between 110 and with 800, if I touch the transistor, for example, to increase its temperature and do a test again, it's now 401. For example, for this transistor, it can differ in the same reference between a transistor and another. This one has a 300 coefficient of the amplification. So to use a transistor, we must know the voltage from the collector to the base, and from the collector to the emitter. This is the maximum rating voltage, and also the collector current, the maximum current that can a transistor handle. This one, EC. For example, here we have a maximum current of 400 milliamp. Also, we can the transistor differ from the maximum frequency. For example, this one, BFR 96, is for the high frequency radio frequency transistor. It can go to the 800 megahertz, for example. Here we can find this outlet transistor in this tuner, for example, this one. Those for the high frequency range. To understand the relationship between the base current and the collector current, I made this circuit. Here we have the plus VCC 6 volt. It goes to the first ampere meter. This one will give us the collector current. And here we have the liter trimmer connected via this liter ampere meter. It will measure the base current. This resistor 10 kilo ohm to limit the base current when this trimmer goes up to the plus VCC. And here we have a voltmeter to measure the base voltage, VBE. Here we can find the schematic. We can find the circuit in this breadboard. We have here the trimmer. Here our 10 key resistor, here a transistor, 2SC3964. Here the little bulb, it's a 6 volt 1 watt bulb. And this one is the voltmeter. Now I will increase the current, the base current, and see how the collector current behave. We can reduce the zoom to see all the parameters. Now I will increase slowly this trimmer, and we will see the base voltage. Here the base current, and here the collector current. the transistor will conduct if the voltage here in the VBE reach 0.6 volt almost. Now I will increase the voltage. Here we have 0.4 volt, 0.5 volt. Here we have the, after 0.5 volt, the EB, the base current, will grow, and the collector current will do the same thing. With a little variation of the base current, we have a great variation in the collector current, as you can see. Here we can adjust the brightness of the bulb. The brightness will tell us about the collector current. Here the collector current reaches the maximum value, 120 milliamp. At this moment, if we increase the base current, the collector current remain stable. So we reach the saturation region of the transistor. As you can see here, I can vary the base current, but the collector current is the maximum value. And the voltage of the base junction, base to emitter junction, it remains 0.7 volt. As you can see here, we have a linear relationship as IC equal to beta multiplied by the IB. But in this region, we have a saturation. No matter I increase the base current, the collector current remains stable. If we trace a curve here between the IC and IB, we will find this one. This is the amplified region, linear region, and here we have the saturation. Here is saturation, about 120 milliamp. The saturation current, it depends on the load here. In this case, we have a bulb here. So here we have the IC, and here we have the IB. We have IC in this region equal to beta multiplied by the IB, the base current. We can calculate the coefficient beta or hash of E, but when we calculate the coefficient, we must take a measurement here in this part of the curve, not in this region. I will decrease the IB until I will have a relationship between the two currents. For example, here we have 500 milliamp, so we have here 50 milliamp. I will choose the best part. Now I will, the full range here is 50 microamp, so I will try to find 40 microamp. For the analog meter, always adjust the range to read the value in this region, not in this low region, to get more precision. Here we will adjust to 40 microamp, and we can see here that we have almost 48 microamp. So I will do the calculation. We have here 48 milliamp. We have the region, the milliamp over 40 microamp, 0.4 milliamp. We have 1,200. This is the coefficient of the amplification of the transistor. I will measure this coefficient with this tester. If we can, I have the data sheet here. Here we can see that they said minimum of 500 here, the beta, the hash of E. We found 1200. I will now close the circuit, turn off the circuit. I will measure this coefficient. We have 1.15K. So we are near our result, 1150. Now I will replace this transistor with a MOSFET, and we will see how the MOSFET behave versus the BJT transistor. I will put the MOSFET here. So in this region I have a MOSFET here. I will do this MOSFET in the place. This VBE will become VGS. We have here the gate, the source, and the drain. So we will measure the VGS. With the VGS reach the VGS threshold, the minimum value of the VGS, this MOSFET will conduct. But we will see that we will measure no current here, amount 0, because the MOSFET has a great impedance, input impedance. Now I will turn on the power supply, which is set to 6 volt. Here we measure in the microamp value. I will start from 0 volt, and we will see in which voltage the bulb will light. 0.7, 0.4, 2, 3. We see here that the MOSFET will conduct when the VGS reach 3 volt. Over 3 volt, we have a little current here, but it's not enough to light this bulb. We see that the drain current, we have a variation here. Now after 4 volt, 3.8 volt, the MOSFET will be conducted. It is on state here. As we can see, we barely see a little current here. It's less than 1 microamp. We barely see a little variation. Now I will test this MOSFET in the component tester. This MOSFET is the ERF 840. ERF 840. We see that the threshold voltage here is 3.2 volt. Now we come to the end of this video. Thank you for watching and have a nice time.